Good morning, dear students. My name is Ferhan Mazher, and the subject today we are studying is Cambridge O Levels Physics 5054. Today we have set our hearts to solve alternative to practical, which we call ATP, or we also call it paper 4. So for this purpose, today we have selected May-June 2011 4-2 paper. This ATP paper, this paper 4 belongs from the zone 2 or the variant 2. In this video, we will have the solution of this paper. So let's start today's paper. So here we go. May-June 2011 4-2 paper. The time allowed for this paper is 1 hour. Question number 1. A student investigates the motion of a toy car down a ramp. The toy car is released from rest on the ramp at the position 1 as shown in the figure 1.1. The toy car leaves the ramp at position 2. It travels the distance d along the floor and comes to rest at the position 3. The distance d is between 1 and 2 meters. Okay, so basically this is the ramp, this is the toy car. So you release this car here at the ramp, and the car comes down, and at the position 2 it leaves the ramp, and then it starts moving horizontally on this floor, and at position 3 it stops. So it covered a distance small d on this floor. Suggest a method for measuring the d. Okay, so if you want to measure this distance d, which is between 1 and 2 meters, so you can use a meter rule. You can also use a measuring tape. So my answer is use a measuring tape. So you can use 2-meter rules, end-to-end measuring tape, or one rule and mark. Okay, so it's better to say measuring tape. Okay, so the next question they are asked, describe how the student ensures that the toy car is released from the same point on the ramp each time. So for example, on this ramp where its front wheels are, okay, so on the ramp, with the help of a marker or a spray paint, make a mark on the ramp. And every time you release this toy car on the ramp, put the front wheels on that mark. So in this way, it's possible for you to always release the car from the same point on the ramp. So my answer is make a mark on the ramp with the marker. Always release the car when its front wheels are on that mark. That's my answer. So this is the marking scheme. Okay. Then the question is on the figure 1.1, mark the height, small h, through which the toy car falls from position 1 to position 2. So this is the height, and so I will mark this vertical height. So let me show you. So you can see I have marked this vertical height and I've labeled it as small h. This is the answer. Okay. So So it should be here, okay? Make it here. Then the question is, the student releases the toy car from the same point on the ramp 5 times and measure D each time. D is this distance, okay? So he's measuring this distance. The student obtains the following values of the D in the centimeter. That's 180, 179, 171, 172, 174. Calculate the D average, the average value for the D. Give your answer to a suitable number of significant figures. So in your data, we have 3 significant figures. So when you will write your answer, that should also be in 3 significant figures. So the method is very simple. You will simply add them, and there are 5 observations. So you will divide the sum with the 5. So it will be 175.2. So in 3 significant figures, it will be 175 centimeter. So this is the exact answer. Okay. Suggest a reason why the results of D vary. You see, sometimes the D value is 171, other times it is 179, 180. So this is a difference of approximately 9 centimeters. So the reason can be because you see, when you release the car here, sometimes I think the student has given, it has released the car gently. Sometimes I think when he released the car, he gave it a little jerk or little push. So when you gave the car a little push, obviously the car will cover a longer distance on the floor. Little push might have been given to car when it was released. So this is the answer showing up on your screen. You can read it. These are alternate answers also. Okay. Then he says, by adjusting the angle of the ramp, the student repeats the experiment for different values of the height h. The results obtained for h and the d average are recorded in the figure 1.2. So this is the height from which the vertical height from which the car is released. And this is the d average value. So when the height is 22, the d is 124. When it's 20, it is 109. When it's 18, it's 94. When it's 16, it is 84. It's 14, it is 70. It's 12, it's 55. It's 10, it's 44. On the figure 1.3, plot the graph of the D average in centimeters on the y-axis. So the D value, this value will be on the y-axis. This will be on the y-axis. And the H value, this value, will be on the x-axis. Your H value is maximum 22. And the D average value is going up to 124. Okay. So 22 means this can be 5, 10, 15, 20, 25, 30. So, and your D average goes up to 124. So it can be 10. Let me reduce the size so you can see it. But this becomes too small. Okay. So it can be 10, 20, 30, 40, 50, 60, 70. And it will not be like this. It cannot be like this. Then it can be 20, 40, 60, 80, 100, and 120. Okay, so let me show you my, okay. Okay. So here is the solution. I have on the x-axis shown the H in centimeter. This is called the labeling. There's 5, 10, 15, 20, 25, 30. On the y-axis, I have represented the D average, which is in centimeters. So 2 centimeter represents 20, 20, 40, 60, 80, 100, 20, 140. So now we will plot the points. So you can see at 22, you have 124. At 22, this will be 22 will be here. you have 124. So this is the dot. And at 20, you have 109. So at 20, we will have 109. I will put a dot here. Okay. At 18, you have 94. So the 18 is here. This is the 18. So you will have how much? 94. Yeah, put a dot here. And at 16, you have 84. At 16 will be this one. It will be 84. Yeah. And at 14, it's 70. At 14, it is 70. So I'll put a dot here. Okay. And at 12, it's 55. So the 12 is this. At 12 is 55. Put a dot here. And at 10, it's 44. At 10, it is 44. Put a dot here. Then they ask us to draw the line of the best fit. Okay, so these are the points. So what I will do, let me show you. So what I will do, I will draw the line of best fit. So this is the pattern in which I draw the line. So I make sure that if the dot is one point is above the line, one point should be below the line. The number of points which are left above the line, the number of points which are left below the line, they should be equal. So approximately this is the line. And the important thing is this is not passing from the origin. Okay. So this is not passing from the origin. So this is that graph. Okay. So now the question is, describe the relationship between the D average and the H. You see, if you look at this graph, they have a linear relationship. As the H value is increasing, the D average value is increasing. And it's a straight line, positive gradient. So it's a linear relationship between them. As the H increases, the D increases. But don't say that they are directly proportional. Why? Because this graph has not passed through the origin. Okay, so that's the reason. So we will say as the H increases, the D average increases, they have linear relation. You see, I have not used the word directly proportional because the graph was a positive slope, it was a straight line, but it was not passing through the regions. That's why I'm not using the word directly proportional. I'm simply saying that as the H increases, D average increases, so they have a linear relationship. You can see this marking scheme for the graph, and this is the answer. Okay. The car is now released from the H 2 centimeter. Use your graph to state what happens to the car. Okay, so when this is the height and this is the D average. So if I will release the car from 2 centimeters, this is the 2 centimeter, this is 2 centimeter. The D average is 0. Okay, the graph is not on 2 centimeters, but I can tell you that the D value will be negative or it is 0. It means if the height, the vertical height is 2 centimeters, so when the car will come down, it will cover no distance on the floor. Simple. The car will stop at the position 2. It will not cover any distance horizontally on the floor. This is my answer. Does not move, stops before reaching point 2, moves to the bottom of the ramp, then stops. Okay. So my dear students, now we are on the question number 2. A student investigates the effect of a converging lens on light from the sun. The student uses a converging lens to produce a clear image of the sun on a piece of white card, as shown in the figure 2.1. So this is the light from the point on the sun. So these are the light rays coming there, and they are focused on this point on this white card. The student measures the perpendicular distance from the center of the lens to the white card. So he measures this distance. Okay. On the figure 2.1, mark this distance and label it S. And then he says, state the name given to this distance. This distance is called, we call it focal length. So they are talking basically about, this is the center of the lens, this is the screen. So this is the perpendicular distance between them. And label it with the S. Put a word here, S. I just forgot to write it here. So write the S here. He asks to label it S. You are supposed to write S here. Then he says, state the name given to this distance. This distance is called focal length. This distance is called focal length. He says, describe in detail the experiment techniques used to obtain an accurate value for this distance. So very simple, what we do, we use a holder which can hold this lens, and we also use a holder which can hold this screen. And we put both these things beside a scale, a ruler, and we move this converging lens forward, backward until a very clear image is formed on this screen. When a very clear and sharp image is formed on the screen, then from the scale, I check what is the distance between the lens and the screen. And that is the focal length of the converging lens. So this is how we do it. So let's see what I have written there. It says, describe and detail the experimental techniques used to obtain an accurate value for this distance. Okay. So if you want to find out very accurately this distance, one technique I told you, that put them in the holders. So when you check the position of the lens and the screen on the scale, your line of sight must be perpendicular to the scale. So in this way, you will avoid the parallax error. Another important thing in every experiment we do is we repeat the experiment. Let's say we repeat the experiment 2 times, 3 times, and each time we find what is the value of the F, and then we take the average value of the F. In this way, a more accurate value can be obtained. His question is, describe in detail the experimental technique used to obtain an accurate value for this distance. Okay, repeat experiment 3 times and take average value of F. Put lens and screen in holders. Move screen forward and backward until clear and sharp images formed on the screen. Avoid parallax error while measuring distance between lens and the screen by keeping the line of sight perpendicular to the scale. Hopefully you understand this answer. A very technical answer. So question number 2, B part, its answer is showing up in the marking scheme on your screen. Okay, so we are going to the next question. It says the 3 resistors A, B, and C are connected in a circuit with the cell as shown in the figure 3.1. So these two, they are parallel to each other, and in series with them is this A. In series with this parallel combination is this resistor A. State the arrangement of the resistor B and C in the circuit. So B and C, they are parallel to each other. So the B and the C are parallel to each other. So Then their question is on the figure 3.1, draw the symbol for a voltmeter to measure the voltage provided by the cell. So if you want to measure the EMF of the cell or the voltage of the cell, so you can put a voltmeter here. Let me show you. I have done that. Okay, so here you see, connect a voltmeter like this. Then their question is on draw an X to indicate the position of an ammeter to measure the current in the resistor A. So if you want to connect an ammeter, so I put an ammeter here. So you can and put a X here. Okay. So you are actually supposed to put an X here. Okay. But I actually made an ammeter there. But you are supposed to put an X here. Okay. But I made an ammeter there. If you read the an X to indicate on figure 3.1, draw an X to indicate the position of an ammeter to measure the current in the resistor A. So this is that position where you will put an ammeter. I have made an actual ammeter there, so, but you are supposed to put an X there. The voltmeter is shown in the figure 3.2. Okay. So state the voltmeter reading V on the figure 3.2. Okay. So we can increase the size to make it more easy for you. So this is 1, this is 2, so there are 5 gaps here. So this is 1.5 volt. So the reading is 1.5 volt. Let's check. 1.5 volt. You see, he said put an X there. Okay, state the voltmeter reading 1.5 volt. That is the reading there. Okay. Then his question is, okay, we're done with this. We're done with this. Okay. He says resistor A, B, and C have resistors. Resistances RA, RB, and RC, where RA and RB and RC, they all are equal to each other, and they are equals to 10 ohm. Use your answer from V in the C first part and the relationship below to find the value of the current I in the resistor A. So I value I want to find out, the voltage value is, we just found it, 1.5 volt. And the RA is 10 and the RC is 10. The RB is also 10, RC is 10, and RB is also 10. You simply have to put the values in this formula. So here we go. So 1.5 divided by I is equals to 10 plus 10 into 10 and divided by 10 plus 10. So it will be 1.5 divided by I. So this is 10. This will be 100. 100 divided by 20, and that will be 5. So it will be 15. So 15 I will be equals to 1.5. So I will be equals to 1.5 divided by 15. So the I value will be 0.1. The I value will be 0.1 ampere. 0.1 ampere. So our answer is right. Then they say 4 students try to build the circuit on the figure 3.1 with the 3 resistors, 10 ohm resistors and a cell. The circuit, their circuit diagrams are shown in the figure 3.1. State and explain which circuit is not the same as the circuits in the figure 3.1. Okay, so which one is not the same? This is same. This is not same. This is same. This one is also same. So circuit number 2 is not same because these 2 resistors, they are not parallel to each other. They are in series with each other. And this third one is parallel to these 2. So this circuit number 2 is not that circuit. Okay. So My answer is coming here. I tried to write this answer. Circuit number 2 is not same. In this, a third resistor is parallel to the two other resistors which are in series with each other. So that one is different. So this second one is different. This is my answer. So let's check the answer from the, okay. So this is question number 3. It's a D parts answer. So now we are on the question number 4. He says the effect of surface color on the cooling of an object is investigated. Figure 4.1 shows two sets of apparatus used in this investigation. So here we have test tube A, here we have test tube B. The outer surface is dull black outer surface. It has hot water, it has thermometer. It also has a thermometer. Its outer surface is shiny silver outer surface. It also has hot water. The test tube, he says the test tube A has a dull black outer surface and test tube B has a shiny silver outer surface. The test tubes containing hot water are allowed to cool. Readings are taken for 20 minutes to allow cooling curves to be plotted. State two factors that must be the same for the two sets of apparatus so that the cooling curves may be compared. You see, the thickness of these test tubes must be same. The material of the test tubes must be same. Their color, outer surface color is different, but their material should be same. Same volume of the hot water they both should have. The initial temperature of the hot water in both of them should be same. And the conditions to which both the test tubes are subject, I mean, they must be placed in the same location and they must have the same temperature of the surrounding. These are some things which should be kept same. Yeah, the opening of the test tubes must be same, the diameter. The diameter of the test tube, conditions of the room, material and thickness of the test tube walls. I think these things should be same. There are many other things. Question number 4A part, the answers are showing up. Hopefully you understand. He says on the figure 4.2, write the headings in the table that is to be used to record the results of the test tube A. Here I will note down the time in minutes, and here I will write the temperature. On the figure 4.3, sketch and label the shape of the cooling curve for test tube A and for the test tube B. You see, the test tube A has dull black outer surface, so its cooling rate will be very fast. So its temperature will drop quickly. Whereas the test tube B, its outer surface is shiny silver, so its rate of cooling will be slow. So its temperature will take longer time to drop. You see the test tube A, its temperature has dropped quickly in less time. The test tube B, its temperature will drop very slowly, relatively slowly. Let me show you the markers. Okay. So the paper is over. So today, my dear students, today we have done May-June 2011 Physics 5054 4-2 paper. This was ATP paper, alternative to practical. This is called paper 4. This paper was from the zone 2 or variant 2. So we were studying Physics 5054, Cambridge O-levels physics. My name is Ferhan Mazher. It's a great blessing for me that I am able to make these videos and touch so many lives of the students. If you have found this video useful, interesting, and it has helped you to do this paper. Please like this video. Please share the link of this video onto your Facebook, Instagram, Twitter, because that will help me promote my channel. Thank you very much. Have a good day. God bless you all.